The moon completes one full orbit around the Earth roughly every 28 days. Looking at a flat, two-dimensional model of the solar system, this cycle suggests a very clear expectation. The moon passes between the Earth and the Sun, and then 14 days later, it slips directly behind the Earth. This geometry should produce two eclipses every single month, a solar eclipse at new moon and a lunar eclipse at full moon. But the observed data contradicts that logic. Instead of 24 monthly alignments, we only see between 4 and 7 actual eclipses globally each year. This extreme rarity made eclipses terrifying to early humanity. Without warning, the sun would vanish from the daytime sky, replaced by a black void and a ghostly, ethereal glow. The moon would undergo a similarly unsettling transformation, turning a deep orange-red in the middle of the night. To the naked eye, these events appear as random, terrifying anomalies. In reality, they are the visible output of a massive, hidden cosmic clockwork. By the 8th century BC, ancient Mesopotamian astronomers realized that these events followed a specific, predictable order. Without telescopes, they relied on meticulous, multi-generational tracking, recording every shadow and phase across the night sky for decades. By documenting these patterns, they effectively reverse-engineered the mechanical predictability of the cosmos from raw observation. To understand the secret they uncovered, we have to look past our flat two-dimensional maps and see the solar system in 3 dimensions. We need to shift our perspective from a flat diagram to a 3-dimensional model of space. The moon's orbit is tilted 5.1 degrees relative to Earth's orbital plane, the ecliptic. Because of this, the moon's shadow almost always misses Earth, sailing above or below the poles. Only at 2 exact intersection points, called nodes, do the planes cross. An eclipse can only occur when a new or full moon happens exactly as the moon is crossing one of these nodes. This creates brief eclipse seasons roughly twice a year. The rarity of an eclipse is the result of strict 3D geometric probability, the difficulty of hitting a moving target in the vastness of space. These orbital mechanics constantly shift. The gravitational pull of the Sun and Earth tugs at the moon, causing its entire orbital ring to slowly wobble. This wobble forces the line connecting the nodes to rotate backwards, completing one full rotation every 18.6 years. The ancient Mesopotamians identified a period where these separate gears finally sync up, the Saros cycle. It lasts exactly 6,585 days. After 18 years and 11 days, the Earth, Sun, and Moon return to almost identical relative positions. The exact same eclipse repeats itself. By identifying the Saros cycle, ancient civilizations gained the ability to forecast future events by looking at the past, using geometry to anticipate the movements of the sky. Once the mechanical alignment is established, the specific visuals we see from the ground are dictated by distance and atmospheric optics. When the moon is fully in Earth's shadow, the Earth's atmosphere bends the longest wavelengths of sunlight, the reds, into the dark center. This Rayleigh scattering creates the deep hue of the blood moon. During a solar eclipse, a moon slightly further from Earth cannot completely cover the sun's disk. This creates a thin, glowing ring of fire. Right before totality, sunlight shines through deep lunar valleys on the edge of the moon, creating bright points of light called Bailey's beads. The visual spectacle of an eclipse is a massive projection of Earth's atmosphere and the moon's physical topography onto the sky. In the 19th century, scientists realized that their perfectly calculated mathematical models for eclipse times did not match the historical records of ancient observers. Historical eclipses occurred about 3 hours earlier, landing 45 degrees further east than modern math predicted. This discrepancy revealed that tidal friction from the Earth's oceans is acting as a planetary brake, slowing our rotation down by a few milliseconds every century. The meticulous observations of ancient astronomers became the data modern geophysicists needed to prove the Earth is slowing down. The 5.1-degree tilt ensures that celestial alignments remain rare, awe-inspiring events that connect our ancient past to the distant future. If you've ever stood outside to watch a total lunar eclipse, you know the main event is that striking, deep red color. But the exact lighting conditions required to create a blood moon aren't rare at all. They're happening right now, today, and every single day. Earth is constantly bombarded by a harsh stream of white light from the sun. Before that light can pass by us and continue into the void, our atmosphere acts as a massive optical filter. This process is called Rayleigh scattering. As sunlight hits the atmosphere, gas molecules scatter the shorter, blue wavelengths of light in all directions, creating our blue daytime sky, while the longer red and orange wavelengths pass straight through the edges of the air. Those escaping red wavelengths converge behind the planet, forming a permanent cone of deep crimson shadow. This is the umbra. It trails millions of miles behind Earth, 24 hours a day. Our moon orbits Earth roughly every 28 days. Based on that timeline, the moon should pass through that massive red shadow once a month. If Earth is constantly projecting a red shadow into the solar system, why do we only see a lunar eclipse a few times a year instead of at the end of every single month? The solution lies in the specific geometry of these orbits. The moon and Earth do not travel on the same flat horizontal plane. Earth travels around the sun on a flat geometric path known as the ecliptic plane, but the moon's path around Earth is slightly different. Its orbit is tilted by approximately 5 degrees relative to that flat ecliptic plane. 5 degrees translates to thousands of miles over the distance between Earth and the moon. Because of this tilt, our satellite usually sails safely above or below the red shadow during its full moon phase. The red projection is constant, but the moon is structurally misaligned with the source. This turns what should be a monthly spectacle into a series of cosmic near misses. For an eclipse to actually materialize, those two distinct orbital planes must perfectly intersect at highly specific coordinates. There are exactly 2 physical points in space where the moon's tilted orbital ring crosses through Earth's flat ecliptic plane. Astronomers call these intersection points the nodes. A lunar eclipse only occurs when a full moon coincides with one of these nodes. This alignment forms an exact straight line between the sun, the Earth, and the moon. Because the Earth and moon are always moving, these conditions only align during eclipse seasons, roughly twice a year. These are the only windows where the geometry allows the moon to catch the shadow. The event requires the precise synchronization of these 2 variables, the specific timing of the lunar phase and the exact coordinate of the node crossing. When that synchronization happens, the moon finally plunges into the umbra, acting as a giant cosmic movie screen. That eerie red hue is the light of every sunrise and sunset happening on Earth at that exact moment, filtered by our atmosphere and projected hundreds of thousands of miles across the void. Scientists quantify the exact color and brightness of this glow using a measurement system called the Danjon scale. Mapping the shade of red on this scale provides real-time data about the state of our atmosphere. A darker, browner eclipse can reveal the presence of volcanic aerosols and other particulates currently circulating around the planet. Without that 5-degree orbital tilt, this complex atmospheric reflection would appear every 28 days, becoming a routine part of the lunar cycle. The eclipse acts as a fleeting geometrical accident that reveals a much larger, invisible reality, the breathtaking and continuous projection of our own atmosphere onto the dark of space. Eclipses do not happen every month. The moon's orbit is tilted by about 5 degrees relative to the flat plane where the Earth and sun set, meaning the moon usually passes just above or just below our line of sight. An eclipse only occurs when the moon, Earth, and sun achieve perfect linear alignment at specific intersecting points in space, known as celestial nodes. During this rare alignment, the Earth blocks the incoming sunlight and casts 2 distinct shadows into space, a soft outer shadow called the penumbra and a dense, dark inner core called the umbra. This brief orbital perfection creates a condition where the moon should, by all accounts, vanish. Looking at this diagram, you see the immense scale of Earth's shadow. The umbra cone extends approximately 217 Earth radii into space. The moon, orbiting at only 60 Earth radii away, sits incredibly deep inside this massive zone of total darkness. According to the basic laws of physics, a celestial body caught this deep in another planet's shadow should receive no sunlight. Early astronomers like Johannes Kepler realized that mathematically, the moon should turn pitch black and completely vanish from the sky. But instead of disappearing into the void, the eclipsed moon remains visible, glowing with an eerie, deep red light. With the Earth standing directly between the two bodies, the question remains how any light manages to reach the lunar surface at all. The reason the moon remains visible lies in the thin, gaseous halo surrounding our planet. To understand how this gas lights up the moon, we have to look at sunlight itself, which is actually composed of every color in the visible spectrum. When white sunlight hits the gas molecules in Earth's atmosphere, it triggers a reaction called Rayleigh scattering. Shorter wavelengths, like blue light, scatter in all directions, giving our daytime sky its blue color. Longer wavelengths, specifically reds and oranges, possess the physical properties required to push straight through the atmospheric gas without being scattered away. Our atmosphere acts as a massive optical filter, stripping away the blue light and allowing only the red spectrum to travel onward into space. As this surviving red light travels through the curved edges of our atmosphere, it slows down and changes direction through a process called refraction. As detailed in this diagram, refraction bends the red light inward. It steers light around the physical mass of Earth, directly into the pitch-black umbra cone. That bent red light ultimately travels through space to strike and illuminate the lunar surface. Because this light comes entirely from the extreme edges of the Earth, the red glow on the moon is the combined light of every sunrise and sunset happening on our planet at that exact moment. The lunar disk functions as a global projection screen, catching the light of every sunrise and sunset on the planet simultaneously. Not all total lunar eclipses look identical. The hue of the moon can range dramatically, from a bright, luminous copper to a dark, almost invisible brown. Scientists systematically measure and categorize this chromatic variance using a qualitative scale. As detailed in the abstract of this paper, it is known as the Danjon factor. The specific Danjon number assigned to a blood moon is dictated directly by the atmospheric optical thickness of Earth at the time of the eclipse. The color of the eclipsed moon is a specific, measurable data point about the composition of our planet's atmosphere. Atmospheric optical thickness is heavily influenced by the average column density of aerosols, tiny liquid and solid particles suspended in the air. High aerosol density is tied to massive planetary events, most notably global volcanic eruptions that pump thousands of tons of ash straight into the stratosphere. When Earth's atmosphere is choked with volcanic ash, less red light can refract through it. The result is a significantly darker, more opaque blood moon on the Danjon scale. By observing the moon's hue, scientists can read the immediate geological and atmospheric state of our own planet.